Lesson number 3, loss function, backpropagation, and optimization. Hello. In the previous lesson, we learned how information moves forward through the network, layer by layer, until the output is produced. But a neural network isn't born with knowledge. And the question is, how? The answer starts with the loss function. Its purpose is to measure how far the network's prediction is from the truth, or in other words, the distance between what we want and what we actually get, where what we want is the label of the example and what we get is the network's prediction. If the prediction is accurate, the loss will be low. When the prediction is perfect, the loss will reach its lowest value, which is 0. On the other hand, if the prediction is wrong, the loss will be greater than 0. Let's use an accompanying example of a classification problem. Suppose a model predicts that an email is spam with a probability of 0.9. And in reality, it actually is spam, labeled by the digit 1. The loss here will be low, but if the model predicted 0.2 for the same example, that's a poor prediction and so the loss will be high. One of the most common loss functions for binary classification is cross-entropy. Its formula looks like this. The letter y represents the true outcome, for example 0 or 1, and y hat is the model's prediction. As mentioned, a high loss indicates that the prediction is incorrect. We want to minimize the loss and thereby improve the network's predictions. Let's go back to the example we've been following. We entered data from a legitimate email message, which is marked by the number 1. The network predicted 0.9 since it's a legitimate message. Now, we input the predicted value and the true value into the loss function, which quantifies how wrong the prediction is. In other words, it's not necessarily a direct difference between the desired value and the actual value, but rather a function that represents the change between what we want and what we have. We found that the loss function is different from 0. In other words, the model's performance measurement showed that there's room for improvement. For the network to improve, we need to find a way to adjust the different weights. This is where the process called backpropagation comes into play. The idea is simple. After the network makes a prediction, we calculate the loss. Then, using the chain rule, we determine how each weight in the network affected the loss. This way, we can attribute the error to each of the weights and update them accordingly.
Or as they say, if a weight increases the loss, we penalize it for that and vice versa.
To calculate the weight updates in the network, we use derivatives. The derivative of the loss with respect to each weight tells us something simple. If we change W a little, in which direction will the loss move? If the result is positive, it means that W increases the price and therefore we would actually want to decrease it. If it's negative, the weight actually helps lower the loss, so we want to increase it. In the graph above, we see the price curve as a function of W. The red dot marks the current state, and the red arrow shows the direction of the change. Here, the derivative is positive, so we'll move W to the left, meaning we'll decrease W and thus reduce the loss. This is exactly the idea behind backpropagation. We calculate the effect of each weight on the total loss and make updates that lower the loss step by step, until the network converges to the best result. To update the weights intelligently, we use a process called gradient descent. This is the main learning mechanism of neural networks, where at each step we calculate the direction of decrease of the loss function and move the weights in that direction, hoping to get closer to the minimum. But the important question arises, by how much should we change? And here comes a critical concept, the learning rate, which is denoted by the Greek letter eta. It's a small number that multiplies the gradient, meaning it determines the direction and magnitude of the change. It determines how big each step of the weights will be during the update. We'll come back to this later. Usually, it's common to use small values on the order of 1,000th for the learning rate. Now let's see how each weight is updated and introduce the gradient descent equation. W equals W minus eta times the gradient of L, where W underscore K represents the current weight and W underscore K plus 1 represents the weight at the next step. To calculate W underscore K plus 1, we use W underscore K, the current weight, eta, the learning rate, and the gradient of the loss, nabla L. In other words, the derivative of the cost function with respect to that weight. This process repeats over and over, and it's the core of training the network. The gradients are calculated using backpropagation. To really get a hands-on feel for the learning process, let's look at a simple example. Let's assume our model is linear with just one weight. That is, y hat equals w times x. Here, the prediction is simply the input multiplied by the weight. We'll use the squared error cost function, where L equals y hat minus y squared. To see what learning actually looks like, let's pick the following numbers: x equals 2, y equals 6, and w equals 1. Now let's calculate the prediction. Y hat equals 1 times 2, which is 2. L equals 6 minus 2 squared, which is 16. The derivative of L with respect to W equals 2 times Wx minus y times x, which, after plugging in the numbers, comes out to minus 16. Now we want to put it all together. This means I'll choose eta to be 0.1, and we'll calculate the new W as the current W minus eta times the derivative of L with respect to W. Plugging in all the numbers, we get that the new W equals 1 minus 0.1 times minus 16, which is 2.6. To sum up, the loss function measures how much the model was wrong. Backpropagation sends the error back. The derivatives determine the direction of the correction. The learning rate controls the size of the step taken during the optimization process. Gradient descent updates the weights. In the next lesson, we'll see how training progresses over time and which techniques help improve the model's accuracy and stability.